So, how do you model a problem that isn't a straight line? Honestly, it's the fundamental hurdle we hit whenever we push the limits of basic machine learning. Because in the real world, data is incredibly messy. Just think about a self driving car trying to distinguish a pedestrian from a shadow on a rainy street. That data curves, it clusters, it intersects. You just can't always draw a simple, neat straight line through it to separate, say, the spam from the inbox, or a malignant tumor from a benign one. So, what happens when our standard linear models run completely out of steam? Well, we have to look toward a system inspired by the human brain itself. Welcome to This Explainer. Today, we are demystifying neural networks. These are literally the engines running our modern world right now, from Siri on your phone to some really massive breakthroughs in medical diagnoses. We're going to break down exactly how these incredible architectures automatically learn complex nonlinear patterns entirely with us having to manually handhold them through the data. All right, let's dive right into this. Here's a quick look at our roadmap for today. 1. The nonlinear world. 2. The anatomy of a neural net. 3. Activation functions. 4. Learning with backpropagation. And 5. Making multiple choices. Okay, starting off with part 1, the nonlinear world beyond straight lines. The stark contrast in efficiency here is just incredible. Remember the dark ages when we relied solely on standard linear models? To capture a curved shape or a complex boundary, we had to manually construct synthetic features. You were literally taking feature x1 and multiplying it by x2 just to force the model to learn a hyperbolic shape. It was tedious manual labor. But with neural networks, that completely vanishes. The network basically acts as an automated feature crossing machine, discovering all those nonlinear relationships completely on its own during the training phase. Moving right along to part 2, anatomy of a neural net. Building the machine. The secret sauce of all this begins with the hidden layer. This is an additional layer of nodes, or neurons, positioned right between your input layer and your final output layer. Instead of just a single combination of inputs to produce an output, this hidden layer recombines our inputs, which significantly increases the number of parameters. And here's why this is absolutely crucial. When you hear that famous buzzword deep learning, well, this is the deep. Deep networks simply stack multiple hidden layers, with each subsequent layer effectively learning a much more complex, higher-level function over those raw inputs. So you might be wondering, what is actually happening inside each of these individual neurons? Surprisingly, it's just simple math. For each node, we take the sum of its inputs multiplied by a unique weight parameter, and then we just add a bias. That's literally it. Inputs times weights plus bias. It is the exact same fundamental calculation as the output of a standard linear model. But wait a second, if a neuron is just doing linear math, how on earth do we solve our nonlinear problem? Which brings us nicely to part 3. Activation functions explained. The secret weapon. See, if you just stack hidden layers that only do linear math, you still just have one giant linear model at the end of the day. It's kind of like multiplying two straight lines together. You just get another straight line. To break this chain and actually learn those curved, complex relationships we talked about, we absolutely must introduce a new step. We insert nonlinear mathematical operations called activation functions into the model right after the neuron's calculation, but before passing the value to the next layer. Without this spark, the whole architecture just falls flat. Let's look at the 3 most common activation functions you are going to encounter. First up, sigmoid. This is that classic S-shaped curve that rigidly squishes any input into a value exactly between 0 and 1. Next is tanh, or hyperbolic tangent. You can think of it as sigmoid's taller cousin, stretching the output between -1 and +1. And finally, ReLU, or rectified linear unit. ReLU is like a ruthless bouncer. If your input value is less than 0, you get 0. If it's 0 or positive, you get to pass right through unchanged. Over time, developers have largely shifted their preference here. While sigmoid and tanh give you these beautiful, smooth, continuous S-curves, they are highly susceptible to the vanishing gradient problem, which we'll definitely touch on in a moment. ReLU, on the other hand, is an absolute mathematical breeze. Because its formula is essentially just the max of 0 and x, it prevents those vanishing gradients and allows a network to train much, much more efficiently. The one caveat? It risks causing dead units. These are zombie neurons that drop below 0 and literally just get stuck there forever. But honestly, even with that risk, modern ML engineers highly recommend starting your models with ReLU. All right, part 4, learning with backpropagation, the supreme ordeal. Backpropagation is the true engine of learning. It is the primary algorithm that makes gradient descent feasible for these multi-layer networks. It uses the calculus concept of gradients to adjust the model's weights by moving backward from the final output. It's essentially apportioning blame for incorrect predictions to the different nodes in order to minimize loss. Now, I know words like calculus and gradients sound super intimidating, but thankfully, libraries like TensorFlow handle all the underlying math for us automatically. Conceptually, though, you really need to know what's happening under the hood. To really grasp this, let's use a quick classroom analogy. Imagine you're a teacher, and you assign a row of students to identify a photograph of a tree. The students in the back look at it, they pass their guesses forward, until Jabari at the very front proudly announces the final group answer, it's a maple tree. But he's wrong. So you, the teacher, walk backward from the front row to the back row to troubleshoot. You realize one student, Ha'u, relied way too heavily on Daniel's wrong guess and completely ignored Fatima's correct insight. So you tell them to adjust how much they listen to each other. You are adjusting their relative influence, their weights. You do this row by row backwards. That is exactly what backpropagation does with math. But hey, training isn't always smooth sailing. There are 3 occupational hazards you really need to watch out for. First, vanishing gradients. In deep networks, the gradients for lower layers can shrink all the way to 0, meaning those lower layers completely stop learning. The fix? Use ReLU. Second, exploding gradients. If weights get too large, the math spirals out of control, and the model basically shatters. You fix this by lowering the learning rate or using batch normalization. Finally, dead ReLUs. Like we mentioned, if a unit's sum falls below 0, it outputs 0 forever, killing the gradient flow. If your network flatlines, try lowering your learning rate or using a variant like LiReLU. And what if your model is learning almost too well and just memorizing the training data? You use a clever trick called dropout regularization. By randomly turning off a percentage of neurons for a single training step, you purposefully introduce a little bit of chaos. It's kind of like forcing a sports team to practice with random players blindfolded. It forces the rest of the team to step up and not overly rely on just one superstar node. This prevents overfitting and makes the final model far more robust in the real world. And finally, part 5, making multiple choices beyond yes or no. So if you have multiple categories, say you want to identify an image as an apple, a bear, a piece of candy, a dog, or an egg, you basically have 2 main approaches. The first is one versus all. This is the brute force method. You train a completely separate binary classifier for every single possible outcome. Is it an apple? Yes or no? Is it a dog? Yes or no? As you can guess, this is incredibly inefficient when you start getting into hundreds of classes. The modern elegant solution is softmax, also known as one versus one. Softmax utilizes a single layer to calculate relative decimal probabilities for every single class at the exact same time. What's really elegant here is the specific constraint that softmax introduces. By extending the formula for logistic regression across multiple classes, softmax guarantees that all the probability values will sum to exactly 1.0, or 100%. Notice how it evaluates a fruit image. A 10% chance it's an apple, 20% orange, 7% grape, and 63% pear. This interconnected constraint helps the model's training converge so much faster than if it were evaluating every single fruit independently. But we do run into a scaling issue. Full softmax calculates a probability for every possible class. If you're classifying millions of items, that becomes computationally exhausting. The workaround for this is candidate sampling. This variant calculates probabilities for the positive labels, but only tests against a random, smaller sample of the negative labels, just to save processing power. And there is one final vital constraint to remember. Softmax assumes there is only one correct label per example. If you hand the network a picture of a fruit bowl containing apples and oranges, softmax breaks down. For multi-label images, you actually must revert back to using multiple logistic regressions. So we've covered the hidden layers, the nonlinear magic of activation functions, the backward-flowing teacher that is backpropagation, and the elegant probability scaling of softmax. Your neural network can now see the complex, nonlinear world as it truly is. So the question I leave you with today, now that you know how the machine learns, what will you teach it to recognize first? Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.